Hello everyone, welcome to my physics channel. And in this video, I'll be discussing tensor analysis. Okay? It's a very important topic if you are going for interviews and all, and it especially helps in relativistic quantum mechanics. Right? So yeah, so I'll be starting this chapter. This is tensor analysis. It's very important and it's a bit tricky, but we'll try to understand. Okay. So yeah. So first let's write a general rule of transformation. General rule of transformation of coordinate differentials. Of coordinate differentials. General rule of transformation of coordinate differentials. So we'll directly jump into the topic. Okay, we'll not mess around. So tensor analysis. Okay. So consider two reference frames. Okay, we'll consider two reference frames. First reference frame is suppose sigma. Okay, another reference frame is sigma dash. This is using summation signs. Okay, I'm taking this as two reference frames. One is some sigma, one is sigma dash. Okay, suppose there are coordinates. I will take coordinates. Suppose x x dash mu. Okay, if I take this coordinate and if I write the expanded version x dash 0, x dash 1, x dash 2, x dash 3, right? So this is the coordinate in sigma dash. This is related to the coordinates of x mu, okay, which is just simply sigma, which I can write as x mu as x naught, x1, x2, and x3. All right. So this is somehow related to this, and how it is related, we will use a transformation to relate these two different strings. Okay, we usually take S and S dash in relativity. Okay, two reference frames, but I'm taking a sigma and sigma as. Okay, it doesn't matter, and we can always connect two reference frames through some coordinate transformation. So here we will also use this transformation. I will write the transformation as x dash mu is equal to x mu. Okay, x mu of x naught, x1, x2, x3. So this x naught is basically the first this one zeroth component, that is we usually write as IC speed. C is the speed of light, T is time, and yeah. So here mu, this mu can be written as 0, 1, 2, 3. Okay, this is the transformation. Then the necessary and sufficient condition that the four components of x dash mu, okay, form a set of independent real functions of this one, is that their Jacobian should not be 0. Okay, so this is completely, I'm directly going into tensor analysis. Okay, I'm not like giving any introduction of it. I hope you have studied some form of tensor. Okay, so I'm directly going into that. So we can write down the necessary. We can write down the necessary and sufficient conditions. The necessary and sufficient conditions that sufficient conditions that the four components that the four components of x dash mu form form a set of independent real functions independent real functions of x0, x1, x2, and x3. Okay, is that their Jacobian should not be 0. Is that their Jacobian, you must have studied Jacobian matrix in our determinant. So Jacobian of transformation of x to x dash. Okay, it will be like del x dash by del x is equal to, how will I write the Jacobian? See, del x dash 0 by del x 0, okay, dot dot dot, del x dash 3 divided by del x 3, okay, and in this side it will be del x dash 0 by del x 3 and del x dash um, del x dash 3, sorry, this one I made a mistake here, this is 0, del x dash 3 by del x 3, okay. So okay, let me write, if you didn't understand, let me write it in an expanded form, this Jacobian del x dash by del x, so it will be something like, first will be what, del x dash 0 divided by del x 0. So everything in this row is the denominator will be 0. Okay, del x dash 1 divided by del x 1 del x 0, del x dash 2 divided by del x 0, and del x dash 3 divided by del x 0. Okay, now this one will be del x dash 1 divided by, sorry, this is del x dash 0 divided by del x 1, del x dash 1 divided by del x 1, del x dash 2 divided by del x 1, del x dash 3 divided by del x 1, right? And this one will be del x dash 0 divided by del x 2, del x dash 1 divided by del x 2, everything will be del x 2 in the denominator, uh, 2 divided by del x 2, and del x dash 3 divided by del x 2, okay. And the final row will be, there is no space here, so let me write it here, del x dash 0 divided by del x 3, del x dash 1 divided by del x 3, del x dash 2 divided by del x 3, and del x dash 3 divided by del x 3. Okay, so this is your Jacobian, and it should not be 0. It should not be 0 for what? This is sufficient in the necessary condition that the four components of x dash mu form a set of independent real functions. This one. Okay, so that the Jacobian should not be. In such cases, what will we do? We can have the inverse coordinate transformation. Okay, what is inverse coordinate transformation? X mu is equal to, I will write the exact opposite. X mu is equal to x mu x dash 0, x dash 1, x dash 2, x dash 3. Okay, yeah, just 1 minute. This there is a dash. This is a function. X dash mu is the function of this one, and here is the exact opposite, reverse transformation. Okay, inverse coordinate transformation. Right. Yeah. So at any point in a general space-time, like the direction of a vector in a coordinate frame, suppose a sigma is determined by the coordinate differentials dx mu. Okay. Dx mu shows us what? What direction of a coordinate system? Of a coordinate system, um, coordinate frame. Sorry, coordinate frame. Suppose sigma. Okay. So define in that frame. So in another frame, it will be sigma dash, and the direction will be determined by the associated coordinate differential, that will be dx dash mu, or suppose we say nu. Suppose we change it. This is dx dash nu. So the relation between these coordinate differentials in the two frames can be written by another transformation rules, like dx mu and dx dash nu. Okay, we can write a relation between the transformation relation between these two, and as dx dash mu, okay, is equal to okay, sorry, del x dash nu divided by del x nu into dx, sorry, del x dash mu, my bad, del x dash mu divided by del x nu into del x nu. So this will be the conversion, okay, between this del x dash mu and dx nu. And but we have like dx mu and dx dash nu. Yeah? So I will write it as just exchange the dashes. Dx mu is equal to del x mu divided by del x nu into dx dash nu. Will that be correct? So this one will also be dashed because this one is dashed. That means this one will also be dashed. This is completely your own understanding. How much you can understand from this, like it completely depends on your mind. Okay, everyone has their own thought processes to understand this tensor because it's not that easy. It's not that like straightforward to understand it. So we have to kind of use our own conventions and all. Okay. Okay, so this is our transformation. If I write it again, dx mu is equal to del x mu del x dash nu and dx dash nu. Okay, this is kind of a differential. If you remember, dy is equal to del y by del x into dx, something like that only. It's in this is just symbols are there. Okay, some notations and all. Okay, so if one can be like okay, while carrying out such a transformation, I can also write, suppose see very carefully, del x dash mu, okay, okay, I'm writing this here, divided by del x alpha, del x alpha divided by del x dash nu, okay, is equal to, what can I write this one? I can write the as like this delta Kronecker delta, okay, delta mu nu because mu is up here in the numerator, nu is in the denominator, delta mu nu, right? Suppose if I write the other way around, like if I write del x alpha by del x dash mu, and again here del x dash mu del x beta, then it will be delta alpha beta. Okay. Again, see these two are getting cancelled out, so I am getting like mu nu. These two are getting cancelled out, so I'm getting like alpha beta. So this is the way of understanding. You have to understand it yourself. Okay. Yeah. Sorry. All right. Yeah. So this let's give this a set of equations. It's very important equations. This is equation one. This is equation two. It's completely mathematical. You just have to be careful a bit with those notations, and you'll be easily able to understand it. Okay. Next. So if one considers this del x dash mu divided by del x alpha as a matrix. Suppose this is a what? Suppose this is a matrix. Alright. So the transformation matrix for the transformation from x alpha to the x dash alpha coordinate system, then this del x alpha by del x dash mu is its inverse. Okay, that means the transformation matrix for the inverse transformation from del x dash alpha to x alpha, okay, x alpha coordinate system, like it's the transformation matrix. This is the transformation matrix for this one. Okay, yeah, all right. You can see here, this is one line, this is kind of the inverse of it. So yeah, this is the transformation matrix for the inverse transformation. All right, yeah. I hope you're slowly getting it. Okay, okay. Let me explain again. So for this transformation, this is the matrix. For this transformation, this is the matrix, just the opposite of this one, just the reverse, just the inverse of this one. If you see, so I can let me write it, x alpha to x dash alpha. I can do it by what? I can do it by del x dash mu by del x alpha, right? Del x alpha. Okay, if I do the exact opposite, the inverse transformation, what do we have to use? Just the inverse one, del x alpha by del x dash mu. Correct? Yeah. So this is what it is about. All right. Yeah. So the Jacobians of the transformation and inverse transformation kind of satisfy that these two will give me one, right? So I can like Jacobian will be x to x dash and into Jacobian of x dash to x. And if we see, this will be like del x dash by del x, which is the first one. This is the del x dash by del x, and for this one del x dash by del x, And for x dash to x, this is del x by del x dash, right? Del x by del x dash. Forget the other notations. It's the same kind of thing. So this is 1. Okay, so this is giving me 1. The Jacobian is giving me 1, right? Yeah, alright. So it's not giving me 0, it's giving me 1. Yeah. Okay. So in special relativity, it is used. So the transformation matrices are the what? Lorentz transformation matrices. Okay, and therefore the Jacobian is identically equal to 1 per unit. Okay, so see, I'll write some notation again here. So del x dash mu divided by del x nu. Okay, in special relativity SR, I'm writing. It's written as lambda. Sorry, it's written as lambda mu nu. Okay, it's written as lambda mu nu. Right? Yeah. So Jacobian of x to x dash, Jacobian of x to x dash is equal to del x dash by del x. Okay, is equal to, as I have written here, I can write it as determinant of this determinant sign of this one, determinant of this one, lambda mu nu, which is which is in fact 1. Okay, which is in fact 1. Right. So yeah. So this is the transformation matrices. And these are used basically in special relativity. You have to remember this one especially. Forget this sentence, but this one you have to remember, right? Yeah. Next, let's go to next section, which is definition and characterization of tenses. Definition, definition, and characterization of tenses. Definition and characterizations of tenses. Okay. So tensors of specific rank and type are physical entities associated with a space-time point, like which follow linear homogeneous laws of transformation. So it's basically about transformation. It's all about transformation of matrices or transformation of coordinates. Okay? So we can write these are physical entities. Tensors are, we can write tensors. Tensors are physical entities. Okay, physical entities associated with a space-time point, associated with a space-time point which follow linear homogeneous laws, linear homogeneous laws of of transformation under the transformation of coordinates. Okay, so a tensor carries superscript and subscript indices. One is up, one is down, and the total number of which signifies the so-called rank of the tensor. Okay, so we can say, suppose it's written like this tensor. Okay, it's written something like something like alpha 1, alpha 2, alpha m, and the lower part is written beta 1, beta 2, beta n of x mu. So we can say rank is what? Rank will be m plus n, right? So this will be the rank. M plus n will be the rank of the matrix, right? So in general, each component of a tensor is a function of the coordinates, that is x mu. Okay? So we can write each component of a tensor which component of tensor is a function of the coordinates is a function of the coordinates, that is x mu, as mu is equal to 0, 1, 2, 3. Right. So yeah. So let's next categorize the tensors. First is tensor of rank 0. Tensor of rank 0, which is called a scalar. Which is called a scalar. Okay. So 0 rank 0 tensors are scalars which remain invariant under any transformation of coordinates. Okay. So we can write rank 0 tensors remain invariant remain invariant means even after changing the coordinates, like the final product is same. Okay, remain invariant under the transformation of coordinates. Invariant under the transformation of coordinates. Right. So we can write phi of x nu. Okay. So it remains invariant under coordinate transformation. What? Which coordinate? Under coordinates transformation. Coordinate transformation x mu to x mu dash x dash. Okay. So this remains phi x nu remains your invariant. Okay. So it will be a zero kind of a zero rank tensor. So what happens in special relativity? In special relativity, every case will study how it is used in special relativity. Okay, because that's where our application is. Just studying the mathematical won't help us. Okay, so like a space-time scalar. Suppose we can write a space-time scalar, invariant under Lorentz transformations (LT). Okay, Lorentz transformation is often called a Lorentz scalar. It's called a Lorentz scalar or four scalar. Okay. You must have heard about a four vector. So this one is a four scalar, rank 0 tensor. Suppose the distance squared is an invariant under Lorentz expression. So we can write for example, invariant distance squared is called it like this only the distance squared. Okay, that is s square is equal to c square t square minus x vector. So here your x vector is actually x0, x1, x2, x3. Okay. So it's basically what is it is ct x, y, z, z. Okay. But we in tensor write down like x0, x1, x2, x. And it's in normal we write it as r vector. And in tensor it's just x vector, nothing else. Okay? No need to worry about all these notations. It's just the same kind of thing but represented in a different way. Okay. So this is your scalar. Okay. Rank 0 scalar. Okay. Next is your tensor of rank 1, which is called, you might guess, it is a vector. Tensor of rank 1 is called a vector. So again, rank 1 tensors are vectors, which are again two types. First is your contravariant vector, contravariant vector, and next is your covariant vector, covariant vector. Okay. So first we will study about contravariant vector. First is your contravariant vector. So I will write like this: a alpha of x mu. Okay, everything is up, and then it's called contravariant. So this can be written as a0 x mu, a1 x mu, a2 x mu, and A3 x mu. All right. So the transformation of this A alpha, how it occurs, transforms like the coordinate differentials dx alpha. Okay, under a given coordinate transformation. So if I write it down, the transformation. So A dash mu will be equal to what? Del x dash mu is here, so mu will be here. Okay, and anything that would be outside A alpha. So this is the transformation for A alpha. Okay, yeah, all right. Which is also similar to, we can say this is similar to whatever we have done before, like dx dash mu is equal to mu is here, so here mu will be upside. Okay, and dx alpha into dx alpha. See, it's the exact same thing in place of a, and there is just dx. That's it, right? Okay. So again, how this contravariant vector is used in special relativity. So in what happens in special relativity is the above transformation rule becomes what? Simply dash mu is equal to, if you remember, in special relativity, how do I write this? How do I write this? I have given here. I write this as lambda mu. Okay, so this is the shortcut. We cannot be writing it again and again like this. Okay, so I will write it as simply lambda, lambda. This is capital mu, lambda mu alpha, na? Yeah, lambda mu alpha. See, alpha is here. So alpha will be here so that the up and down can be cancelled out and this mu remains. This is not the explanation. This is just to understand, just to kind of remember the notations. This is not the expression like alpha alpha will be cancelled out mu. No, no. Okay. So this is just the transformation. This is the one that transforms a alpha into a dash mu, right? From one coordinate system to the other. So we can write a contravariant vector is called a space-time 4 vector, or simply 4 vector. Okay, space-time 4 vector or simply a 4 vector. Okay, anything you can say. Okay. So this is a contravariant. Okay, whenever the symbol is in the upper part, it is contra. Okay, whenever it is in the down part like this is your co. Okay, just a way to remember. So this is contravariant. Next is your covariant vector. Covariant vector. Okay, so I took A in the contract, so I will take B here, and took alpha here, I will take beta. So B beta x mu. If I transform it, it will be like B naught x mu, B1 x mu, B2 x mu. Simple. You can write along with me. It will be very easy to understand. B3 x mu. Okay. Yeah. So again, the transformation will be there. Okay, if we transform it, so like b nu dash is equal to so nu is here. Okay, see, del x beta by, see carefully, del x dash nu b beta, right? Yeah, which is kind of similar to what, which if I say, which is kind of similar to del phi del x dash nu is equal to del x beta by del x dash nu and del phi by del x beta. So it's kind of same, right? So again here this is changing. This is the way. This is the one that is transforming, and here beta is here, nu is here. So I can write it again special relativity. So this is nu. This is beta. Okay. So I have to write like that. So in special relativity I will write like b nu dash is equal to lambda nu beta b beta. Okay. So if you see, this nu is here, this is covariant, and this beta beta they will cancel out and make your thing. Okay. Yeah. So covariant vector is also called simply a covector. Okay. So you can write covariant vector is also called a covector. Yeah. So, like one may note by analogy that the ordinary three-dimensional Euclidean space, okay, where the partial derivatives of a scalar phi here, the way we took it, okay, with respect to coordinates x mu, constitute a gradient of the scalar. Okay, is the gradient of the scalar, which points along the normal to the surface phi is equal to constant. We know that. Okay. Accordingly, like components of a covariant vector b beta may be thought of as like the normal or perpendicular. We can think if think it as a normal or perpendicular. Okay, or projections of the vector on the coordinate axis. We can think like that. Okay. By similar reasoning, components of a contravariant vector like this one. Okay, a alpha may be thought as the tangential or parallel. Okay, we can think it as the tangential and the co as the perpendicular one. Okay, projections of the vector on the u coordinate axis. Okay. So let's write this point. So contravariant a alpha can be thought of as a tangential or parallel. If someone asks you like the physical significance of it, you can say that tangential um, uh, parallel projections projections of the vector on the coordinate axis. Okay, coordinate axis. And co-vector, that is your b beta, can be written as what? Normal or perpendicular, normal or perpendicular projections of the vector on the coordinate axis, whatever we had written before. Alright. Okay. So our familiar perception is that the parallel projections like define the components of a vector in the Euclidean three-dimensional space. The parallel projections, that is here the a alpha ones. So we can say it's very convenient to consider that the contravariant vectors, that is your a alpha, will form a vector space in the usual sense, whereas the covariant vector, the b beta, okay, will constitute a dual vector space. Right? Such a duality is, of course, the duality of projection in the coordinate space, and we should not confuse it with like the tensor duality, okay, which we'll discuss later on. Right? Yeah. So this is your tensor of rank one, that is called a vector. So next will be your tensors of rank two, or equals or greater than two. Tensors of rank equal to or greater than two. Okay, so if we okay, here again there are three types. Again, those things are here: contravariant, covariant, and there is another one that is called a mixed tensor here. Contravariant tensor, covariant, and another one is a simply mixed tensor. All right, so we'll study that. Okay, first of all, your contravariant again. Okay, so now it will be simple to understand because we have already done it. Contravariant. Okay, contravariant. So again, it's very simple. So the transformation will be kind of like t dash mu one, mu two, mu m, and this will be lambda, mu one alpha one. It will go on and on, mu m alpha m, okay. T alpha one, alpha m. Suppose if I write only one, okay, t dash mu is equal to lambda mu alpha and your t alpha. That's it. Very simple. Exactly like your previous one, but here the rank is 2 greater than 2. That's why we are writing a lot of stuff. Okay. So yeah. So this is a contravariant. Next is a covariant. Covariant again, same kind of things, right? Same kind of things. And if I directly write it t dash mu one mu two, if you see this part is in the upper part, this is in the lower part. So lambda mu one beta, okay, and this symbol alpha is in the this one, yeah. Here beta is here, and um, lambda mu n beta, and this is simply t beta one up to beta n. Yeah. So this is a covariant, and what will be your mixed tensor? The third one is a mixed tensor. So what is a mixed tensor? Third one is a mixed tensor. What is it? It's of say it should be rank of m plus n. Okay, rank of m plus n, right? Like greater than equal to 2 and n greater than equal to 1, n is greater than equal to, is defined by denoted by what? T alpha 1 alpha 2 dot 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 alpha m, and also beta 1 beta 2 dot 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 beta n, beta n, it is n, this is m, and x mu, okay? And it transforms like a direct product of m contravariant and n covariant vectors, okay? It's very, remember it, m contra and n co. This is the transformation for your mixed tensor, right? So let's see how it is being transformed. Suppose if I write it t dash mu one mu two dot 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 mu m, and the lower part it will be mu one mu two dot 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 mu n. So it will transform like del x dash mu one, okay, del x alpha one dot 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 del x dash mu m, del x alpha n, okay, alpha m, sorry, in into del x dash del x dash beta, okay, sorry, here dash won't be here, del x beta 1 divided by del x dash nu 1. I hope you are slowly getting it, right? It will take time, don't worry, it will take time. Del x dash mu n, okay, yeah, into t alpha 1 alpha n and beta 1 beta n. So uh, this is your mixed answer. I hope slowly you will slowly get an idea, and don't worry about it. Okay. Yeah. All right. So if we write like in special relativity in terms of lambda, okay. So I can write t in special relativity. We write t dash mu one up to mu m. Okay. If you, the thing is, if you write it again and again, you will see that you are slowly starting to understand it. Slowly your brain will start to comprehend what we are writing. Okay. So don't worry, don't panic that these symbols are haunting you or something. No, it's very decodable. Nothing is mu one. Another thing, notice mu one is being written very close to lambda. Here mu one is written very close to lambda. So mu one. These are the important notations for us. Alpha and beta we can like a dummy index or something. We can take them like anything. Okay, mu n and beta n. So they will be written far away from it, and the mu the main notations will be written near to it. Okay, into t alpha 1 again alpha 1 up to alpha n, and mu 1 up to mu n. Alright, so this is a simply mixed tensor and special relativity. Alright, yeah, okay. So let's go to tensor algebra. Okay, we're slowly moving forward. It's not a tough chapter, you just need a bit of practice and a bit of concentration actually. Focus and concentration is what we need in this chapter. It's not like your vector analysis chapter that will just easily swipe away. So simply the first one is your linear combination. Linear combination of tensors. So only tensors of the same rank and type could be added. Okay, this is very important. Only tensors of the same rank and type can be added. Okay, added to produce another tensor of the identical. Yeah. Produce another tensor of identical what rank and type. Okay, all right. Yeah. So the same is true for any linear combination of tensors of the same rank and type. For example, suppose let's take two covariant tensors. Okay, rank two. Suppose one is your a alpha beta covariant tensors. Okay, so the notation should be downside like below. Okay, b alpha beta. So the linear combination will be simply t alpha beta, which will also be below. That means covariant. So t alpha will be phi of a alpha beta plus anything like anything. Take it alpha or phi or psi anything. Okay, b alpha beta. So these two are what? These two will be called space-time scalars. These are simply scalars, and those are rank what? Rank zero. Okay. Yeah. This is exactly the one we used to do in quantum mechanics, where you used to write psi vector is equal to a1 psi 1 plus a2 psi 2. Similar kind of thing. This is also a linear combination of wave functions. Okay, here also linear combination of two covariant vectors. Okay, yeah, of rank two. Yeah, these are rank two. You can see it here, rank two. Yeah. Again, okay. This is your linear combination. Next operation is your multiplication. Multiplication of tensors. Multiplication. Okay, multiplication. Here, like unlike linear combination, multiplication we can have any type and any rank, same or different. It's possible. Okay, we there is no restriction like one should be two and other hash should have rank two. Okay, it can be different also. There is no problem. Okay, so there can be three kinds of tensor products. Again, in products also there are three types. So three types of tensor products. Right. So three types of tensor. First one is called a direct product. First one is called a direct product. Okay. So the aggregate obtained via multiplication of any two tensors, the same or different type. Suppose the ranks m and n is another tensor of rank. No, not m plus n. M plus n. Okay. So the product one will have the rank of m plus n, not m cross n. Suppose let's take an example. Example A alpha, this is contravariant, B beta, this is covariant. Okay, is equal to T alpha beta. Okay, suppose A alpha beta into B gamma. Right, this can be written as T alpha beta gamma. Everything will be contra. Right. So if I take the direct product of them, so it will be like A alpha, B beta gamma. Okay, suppose. Okay, delta. So this will become T alpha beta gamma delta. Okay. So like this is kind of like this one, right? See here, A alpha B beta. These are the same kind of ranks. This rank is not same. See this two rank. This is rank one. We can say something like that, or different types, and we are getting a product. Here also we are getting a product. So there is no problem with that. Okay. This is called direct product. There is next one is called a contracted product. Contracted. This is a contracted product. Okay. So if two different types of tensor to rank m and n have p number of matching contra and covariant indices. Suppose it has like alpha beta gamma one, another has beta gamma. So two. indices are matching with each other. Okay, then the direct product of the tensor reduces to another tensor of rank m plus. So it reduces to m plus n minus 2p, sorry, 2p. M plus n 3 plus 2 minus 2 into 2, the common one. So this is 3 plus 5 minus 4, that is 1. Okay. Yeah, alright, with no matching contra. Yeah. So for example, again, see, A alpha beta, B beta gamma. Okay, so if you see this beta beta are here, so they're matching with each other. They will just kind of vanish. Okay, so it will become T alpha gamma, the one I told you before. Okay, so next suppose A alpha beta. Slowly you will start to enjoy it. Don't worry. Mu nu, A alpha beta mu nu, alpha beta in the contra, mu nu in the co. B gamma delta mu nu. Okay, so mu nu are here, and again see there is no matching here. So mu nu can be cancelled out. We can simply write a tensor of T alpha beta gamma delta. Now I think you are starting to enjoy it. See, it's not that hard. Beta beta cancel. Just think it as cancelled out. Don't think any technicalities and all. Always try to understand your way. Okay, this is mu nu cancelled out. Alpha beta. Okay, yeah. Let's try one more if you're enjoying it. A alpha beta. Okay, gamma. B beta gamma. So what will happen? Tell me. See, gamma gamma cancel out. Beta beta will cancel out. So it will be T alpha. Okay, very simple. See, it's very simple. So this is your what? Contracted product. Okay, this is called your contraction. Simple contraction in tensors. It's very, very. If you understand it, it's very enjoyable. Yeah, you love to kind of cancel things out. So contraction implies a reduction of any mixed tensor of rank n. Okay, reduction of, we can say reduction of any mixed tensor, any mixed tensor of rank n, okay, which is greater than m1. Of course, it should be is m1, with p matching contra and covariant indices to a new tensor of rank n minus 2p. Yeah. But if I give you more examples like t alpha, sorry, t mu, alpha mu, so it will give me what t alpha is here, na? So it will be t alpha mu cancel, t mu alpha mu beta. So see, mu cancel out, so t alpha. But so last one, suppose if I give this example, mu alpha mu, okay, mu beta and mu gamma. Then so here again mu cancel out, alpha beta. So t alpha beta. Okay, don't do this. Okay, this is not exactly what it is, but whatever. Next is just simply scalar product. Okay, simply it will multiply the scalar, which is the outcome of the. Okay, so let me give you some example. You understand. Number three is scalar product. So A dot B can be written as A alpha B alpha. Similarly, okay. S dot T can be written as S alpha beta T alpha beta. Okay, no problem. QR can be written as, suppose Q alpha beta gamma is your R alpha beta gamma will be where? Okay. Yeah. Okay. Next, let's move to next section of this. That is called norm and trace of tensors. Norm and trace of tensors. Norm and trace. What is norm and trace? Very easy thing. Norm of a tensor of any rank is this scalar product with itself. So norm can be written as scalar product, writing in very short, okay, with itself. That is simply norm. Yeah. Suppose A norm is equal to A alpha, A alpha. There is a simple norm. This is the way to write it. Okay. A is alpha beta, A is alpha beta. Yeah. T square, T alpha beta gamma, T alpha beta gamma. Simply the product of itself with itself is called your norm. Okay. And what is trace? Trace is simply we have shown in matrix. So, but here it will be trace of A's alpha beta will be what? A's alpha alpha. I will tell you, don't worry. Trace of T alpha beta gamma delta. Okay, will be T alpha alpha beta beta. So what is it now? What is this? So trace is defined only for tensors of even rank. Okay, only for even rank is greater than 2, greater than equal to 2. Trace is the full contraction of the indices of the even rank also. Next. Okay. So we'll study about it later. Don't worry. Okay. Okay. So this is a trace. Next, right now, just I will give you an introduction of a metric tensor, which we will study in the next class. Just a brief introduction of it. The metric tensor, which is very important. Okay. So suppose um, in relativity, like uh, this d square, the square distance square element, it's invariant. Okay. So invariant. We can write it as d square. It's kind of like this. So dx1 square, dx2 square, dx3 square plus yeah this much more. Okay. This is but this one is in three-dimensional Euclidean space. This is not in your Lorentz. Okay, this is only three-dimensional. So in Lorentz transformations or Lorentz or like this is also called Poincare transformations. So in Lorentz transformations, what happens? It becomes four coordinates. Okay, four-dimensional Minkowski space-time is used. So ds square will be dx naught square minus dx1. Why it is minus also we'll study. Dx2 square minus dx3 square. Yeah, alright. So this ds square is quadratic in the differentials of the coordinates what? Suppose we can let's say dx alpha where alpha is your simply 0, 1, 2, 3. One we can also express this one as very important. D square is equal to g alpha beta. See carefully. Dx alpha dx beta. Okay, yeah. G alpha beta dx alpha beta. When alpha is equal to beta, it will have a value, and this will dx zero. So this alpha is zero. G zero. This is dx zero dx zero square, and dg zero zero is one. Okay, but thing gets complicated. Suppose alpha is minus one. So what will happen? This thing will become sorry. Alpha is one. Sorry. So G11 is actually minus one. Okay. So this thing that's why this minus is coming here. Alright? Yeah, it's kind of written like this. Minus one, minus one, minus one. This is 0, 0. This is a metric tensor. We'll study it the next class. Okay. Alright. So next class we'll study metric tensor, and that will be the class. We'll finish this topic, but that's not the end. The main part is the application of it in relativistic quantum mechanics and relativistic electrodynamics. Alright, in particle physics, all those things are there. We'll study slowly, alright, which will really help you in your interviews. Because these things don't come in entrance exams, they will only come in interviews. And yeah, I hope so. It will help. It has helped you today because I've tried to completely explain in the most layman manner, like easiest way, because that's the way I understood it. So I try to teach you in that way only, because teaching, studying this in a very high quality, like hi-fi method doesn't work. It should be simple and precise, the way one should understand. Okay, so yeah, that should be it for this class. See you tomorrow in another video. Okay, thank you very much. Thank you.